Perfect. Thank you. So good afternoon, everyone. I'm Zancato Elena, and I'm a master's student at the University of Padua, and I will present my research about an experimental evaluation of the fatigue notch factor in as-built specimens produced by wire and arc additive manufacturing. Wire and arc is one of the techniques included among the additive manufacturing techniques, and as we all know, these kind of procedures, the processes have a lot of advantages in their use. For example, the freedom of shape and the ability of creating complex geometry with minimal material waste. But in order to keep those advantages, we need to reduce the post-production operations and to use the components in the as-built form as much as possible. To do so, it's important to evaluate the effect that the as-built surface has on the component. In this research, in particular, on the fatigue life of the components. And to do so, we can quantify the notch fatigue factor that, as we all know, is a factor that correlates the behavior of a notch component with the behavior of a fully machined component for vamped components. To do so, I performed several fatigue tests on an axial machine with a load ratio of 0.1 for an experimental valuation. Before performing the tests, however, I also performed some tensile and hardness tests and some microstructural analysis to understand better the behavior of such material. As we can see from the micrographs, we can clearly identify the frontiers of the weld beads, just looking at the heterogeneities of the microstructure, according also to the literature data. We can see some delta ferriti here, and some fine and columnar grain in this part of the materials for two different directions that are parallel to the as-built surface on the upper part, and in the lower part is normal to the directions of the weld. I was then able to estimate, thanks to tensile tests, the stress-strain curves of the material. And as we can see from the property that I was able to evaluate, the component experienced plasticity way before yielding, and its behavior is very ductile. As you can see also there in the table, there are listed other properties for a specimen that's a stainless steel specimen, 308 with low silicium. Then from an as-built plate that you can see on the left that has been printed with a zigzag pattern, in its as-built form, we extracted two kinds of specimen that are here represented as type A specimen and type B specimen, where type A specimen contain as-built surfaces on two sides, so here and on the opposite side, while the grip part is machined, and type B specimen that are fully milled. There is also an innovative feature in the design of these specimens, as you can see here, according to the American standard E466, we adopted an hourglass shape along the width of the specimen, but we also decided to adopt an hourglass shape on the thickness of the specimen, taking this way advantage of the possibilities of the additive manufacturing processes to print complex shape. Here you can kind of see the hourglass shape, and this choice was made because we wanted to avoid the first notch effect that could have happened between the machine part here in the grip and the part containing the as-built surfaces. Both types of component have then been tested on a hydraulic machine with actual test. This machine has a 400 kilonewton capacity. And we applied the load normal to the deposition plane, so normal to the direction of the weld, with a stress range from 140 to 460 megapascal, a load ratio of 0.1, and a frequency of 7 Hertz. The results are the SN curve plotted for the same load ratio in both the as-built and the machine configuration, where we were able to find a slope for the as-built surfaces of 4.21. That's perfectly in accordance with the data from literature that are in a range from 4 to 4.9, and from smooth specimen with a slope of 5.88. From the broken specimen then, it was possible to analyze at the SEM microscope whether the cause of the failure was due to internal defects of the component or to the presence of some notches and defectosity on the as-built surface. And as you can see from these pictures, multiple cracks are propagating from the as-built surface, and there's no sign of internal defects that caused the failure of my specimen. Therefore, I can assume that the major cause of failures is due to the presence of the as-built surface and not of internal defects. So the company claimed that the material could have been defect-free inside, and with the result of those fatigue tests, I can also confirm that they were not, if any defect was present inside of the component, it was not the cause of the failure of the specimen itself. By confronting the two SN curves shown before for the machined and for the specimen containing as-built surfaces, I was able to estimate the stress range that should be applied for a component to reach a target value of 2 million cycles, that for a machine specimen is around 235 megapascal, and for a component containing as-built surfaces is around 103 megapascal. Finding this way, thanks to the ratio between those two values, an experimental fatigue notch factor that's 2.27. This value is perfectly in accordance with the behavior of the butt joints, for whom the fatigue factor, according to literature, is in most cases 2.27. To conclude, in order to evaluate the effect of the as-built surfaces, we were able to see that the cracks in the specimen were actually originating from the as-built surfaces, as you can see also in these other micrographies, as the effect of the surface and of the defectosity present on the surface that we can consider, for example, as multiple notches in series. The quantification of the experimental of the fatigue notch factor between as-built and completely machined surfaces of warmed component is 2.27, as stated also for the butt weld joints. This is the end of my presentation. I thank you so much for the attention.
Thank you, Elena, for the interesting presentation. Is there any questions from the audience? Okay, please, Matteo.
Okay, thank you so much for your nice presentation. Just one curiosity, do you mean that this notch effect in relating the difference between as machine and as built specimens is only related to the elimination of surface roughness, or can be also attributed to introduction of compressive residual stresses during machining?
So I think that it can be also correlated to compressive residual stresses, but during the machining process, we were very, very careful on not trying, at least, not to alter too much the geometry of the components. So we tried to just remove the as-built surfaces without compromising too much the integrity of the rest of the material. So I think that for the most part, the cause of this notch factor is mainly due to the behavior like welds. So this component is clearly more or less like welds, one on top of the other. So as we saw from the broken specimen and also from the behavior, I think that it's mainly correlated to the this behavior of the material connected more as a series of welds, more than compressive tests that could be introduced thanks to the machining process.
Thank you.
Thank you.
Any other question? Yes.
I have also one question from this diagram, which is visible from your presentation. It's possible to see that this notch factor, it's possible to say, is not constant through the whole lifetime region. Could you have you some idea or some explanation of this behavior? Because it will be only geometrical behavior in linear elastic region must be the constant.
Yeah, it's perfectly right. But we also saw that the material is not behaving completely in an elastic way, and it's experienced plasticity at a very low levels of loads. So I think that increase in this region, oh, sorry, I will point again. In this region where the loads are higher, the stress applied are higher, the behavior of the component cannot be thought of as elastic. So the plasticity has some influence in this fact that the curves are not parallel. So the fatigue notch factor changes with respect to the number of cycles where it's evaluated.
Okay, thank you again, Elena.
Thank you.